Chapter 6.1 Reciprocal, Quotient, and Pythagorean Identities. An identity is an equation containing one or more variables that is true for all values for which both sides of the equation are defined. In order to prove that an identity is true, we must use algebraic operations to show that the left side is always equal to the right side. Consider the statement a plus b squared equals a squared plus 2ab plus b squared. If you let a equal 5 and b equal 2, if you substitute these values into each side of the equation, you get the following. A is 5, so on the left side we have 5 plus b is 2. 5 plus 2 squared on the left. On the right side we have a squared, so 5 squared plus 2 times a, which is 5, times b, which is 2, plus b squared, which is 2 squared. On the left side, 5 plus 2 is 7 squared. On the right side, we have 25 plus 5 times 2 is 10, times 2 again is 20, and then 2 squared is 4. On the left side, 7 squared is 49. And on the right side, 25 plus 20 is 45, plus 4 is also 49. So the left side equals the right side. That tells us the statement is true for a equals 5 and b equals 2. This is called a numerical verification, but it does not prove that the statement is an identity. You have shown that the statement is true for certain values of the variables, so it is possibly an identity. We've only shown that it's true for these specific values, a equals 5 and b equals 2, so this is not a proof. In order to prove this statement is an identity, you must use algebra. Here is the proof. On the left side, we had a plus b squared, and on the right side, we had a squared plus 2ab plus b squared. On the left side, a plus b squared is a plus b times a plus b. We can multiply those together using the distributive property. A times a is a squared. A times b is ab, so a squared plus ab. Then b times a is ba or ab. And b times b is b squared. Then I can combine our like terms. We get a squared plus 2ab plus b squared. And then we see that we have the left side is equal to the right side. Therefore, the statement is true for all values of a and b, which means that this is a proof. Note that you only perform operations on one side of the identity until it looks the same as the other side. Now that we have algebraically proven the statement to be true, we can say that the binomial a plus b squared equals a squared plus 2ab plus b squared is an identity that holds true for all real values of a and b. This page is just going over some of the identities and information that's on your formula sheet and also the equivalent forms. Starting with an angle in a circle, we have the point where the terminal arm of the angle meets the circle is the point xy. Then we can create our triangle that has an opposite side from angle theta of y, adjacent side from angle theta is x, and the hypotenuse is the radius of the circle. From that, we get that sine theta equals opposite over hypotenuse, which in this case is y over r. Cos theta is adjacent over hypotenuse, which in the circle is x over r. And tan theta is opposite over adjacent, which in the circle is y over x, where x cannot equal to 0. And then the equation of the circle is x squared plus y squared is equal to the radius squared. That's just using Pythagorean theorem. Then the following fundamental trig identities are developed. We have the reciprocal identities. The following three are on your formula sheet. We have cosecant theta is equal to 1 over sine theta. That's on your formula sheet. What's not on your formula sheet would be the equivalent form that sine theta would be the reciprocal of cosecant theta. So sine theta equals 1 over cosecant theta. On your formula sheet, you have secant theta is the reciprocal of cos, so 1 over cos theta. And from that, you can get that cos theta is equal to 1 over secant theta. Then also on your formula sheet, you have cotan theta equals 1 over tan theta. And from that, you can get tan theta equals the reciprocal of cotan theta, so 1 over cotan theta. We have the quotient identities. Tan theta equals sine theta over cos theta, and cotan theta equals cos theta over sine theta. I believe both of those are on your formula sheet. Then we have the Pythagorean identities. On your formula sheet, you have cos squared theta plus sine squared theta equals 1, or it might say sine squared theta plus cos squared theta equals 1. From that, you can get two different equations. If you isolate sine squared theta, you get sine squared theta equals 1 minus cos squared theta. Or if you isolate cos squared theta, you get cos squared theta equals 1 minus sine squared theta. Also on your formula sheet is 1 plus tan squared theta equals secant squared theta. Again, we can get two different equations from that. If we isolate tan squared theta, we get tan squared theta equals secant squared theta minus 1. And if we isolate 1, we get 1 equals secant squared theta minus tan squared theta. And the final Pythagorean identity on your formula sheet is cotan squared theta plus 1 equals cosecant squared theta. From that, we can get cotan squared theta equals cosecant squared theta minus 1. Or if we isolate the 1, we get 1 equals cosecant squared theta minus cotan squared theta. You're going to need to refer to your formula sheet a lot for this unit. Using identities to simplify expressions. When simplifying trigonometric expressions, we will need to use the fundamental identities along with algebraic manipulations such as multiplying and expanding, factoring, collecting like terms, combining fractions. For each of the following strategies for simplifying trig expressions, show the algebraic version and the trigonometric version. Factoring. So we have the algebraic expression 1 minus x squared. We should recognize that as a difference of squares. A difference of squares factors to two binomials. The first term in each binomial is the square root of the first term of our expression. So square root of 1 is 1. The last term in each binomial is the square root of the second term in our expression. So square root of x squared is x. And then one factor gets a plus and one factor gets a minus. A trigonometric expression that's similar, 1 minus sine squared x. Again, this is a difference of squares. So same thing. two factors. Make your factor a little bigger because we're going to have to write sine x in there. Square root of the first term is 1. It goes at the beginning of each factor. Square root of the last term, sine squared x. If you square root that, you get sine x. That goes at the end of each factor. 1 gets a plus and 1 gets a minus. Next algebraic expression, a squared minus b squared. Again, that's a difference of squares. We factor that to two binomials. The square root of a squared is a, that goes at the beginning of each factor. Square root of b squared is b, that goes at the end of each. One with a plus, one with a minus. The trig expression, secant squared x minus tan squared x. Same thing, also a difference of squares. Two binomials, just make them bigger because we need to fit more into them. Square root of secant squared x is secant x. Square root of tan squared x is tan x. One with a plus and one with a minus. Adding fractions. The algebraic expression is a plus b over c. To add fractions, we need a common denominator. A whole number or a variable can be written as a fraction by putting 1 underneath. We want the denominator to be c, so we multiply by c on top and bottom. Then we get ac over c plus b over c. Now we can add the numerators together. We get ac plus b all over c. The trigonometric expression, sine x plus sine x over cos x. Same thing, we can put sine x over 1 to make it a fraction. We want the denominator to be cos x to match our other fraction, so we multiply top and bottom by cos x. Then we get cos x sine x over cos x plus sine x over cos x. Now that we have the same denominator, we can add our numerators, which gives us cos x sine x plus sine x over cos x. Multiplying by the conjugate, an algebraic expression, we have square root 2 over root 5 plus root 2. The conjugate is the binomial but with the opposite sign, so root 5 minus root 2. We multiply that on top and on bottom, root 5 minus root 2. We have to use distributive property, so multiplying that in, and then this is a binomial times a binomial. Then we get the top, we have root 10 minus root 4. On the bottom, we have root 5 times root 5, which is the square root of 25, or the whole number 5 if you want to jump straight to there. Then we have root 5 times negative root 2, which is negative root 10. Then we have root 2 times root 5, which is positive root 10. And then we have root 2 times negative root 2, which is negative root 4, or just 2 if you want to jump straight to there. We simplify our two middle terms. We'll add to 0, negative root 10 plus root 10. The top becomes root 10 minus 2, square root of 4 is 2. The bottom becomes 5 minus 2, square root of 25 is 5, square root of 4 is 2. We can't simplify square root 10, so we get square root 10 minus 2 on top. And on the bottom, 5 minus 2 is 3. A trig expression, 1 over 1 minus cos x, multiply by the conjugate, 1 plus cos x, and on the top as well, 1 plus cos x. We get the top would just be 1 plus cos x. The bottom, 1 times 1 is 1. 1 times cos x is cos x. Negative cos x times 1 is negative cos x. And negative cos x times cos x is negative cos squared x. The middle terms add to 0, cos x and negative cos x. We're left with 1 plus cos x over 1 minus cos squared x. Then if we look at our denominator, we have 1 minus cos squared x, which is a difference of squares. So we can factor that. The top remains 1 plus cos x. The bottom becomes 2 binomials, both starting with 1, both ending with cos x, one with a plus and one with a minus. Then we see that we have 1 plus cos x on top and 1 plus cos x on bottom. We can divide those factors out, and we're left with 1 over 1 minus cos x. Use x, y, and r to show the following. First one, cotan theta equals cos theta over sine theta. Normally we would only manipulate one side of the identity to show that it equals the other side, but in this case we want to use x, y, and r, so we're going to manipulate both sides of the identity. I'm going to start by drawing an angle in standard position in a circle. Our angle theta, the terminal arm meets the circle at the point x, y. The length of the terminal arm is the radius. We can draw a right triangle by going straight down from point xy to the x-axis. Then the side opposite from theta is y, and the side adjacent to theta is x. On the left side, we have cotan theta. Cotan theta equals 1 over tan theta. But tan theta is opposite over adjacent, so that is 1 over opposite over adjacent, which is 1 over, from our circle, the opposite side is y, the adjacent side is x, so 1 over y over x. When we divide by a fraction, we multiply by the reciprocal, so we get 1 times x over y, which then gives us x over y. On the right side, we have cos theta over sine theta. Cos theta is adjacent over hypotenuse, and sine theta is opposite over hypotenuse, so we get adjacent over hypotenuse divided by opposite over hypotenuse. From our circle, adjacent is x, hypotenuse is r, opposite is y, hypotenuse is r, so we get x over r divided by y over r. Then to divide fractions, we multiply by the reciprocal, so x over r times r over y. The r's would divide out, and we would be left with x over y. Then we see that the left side equals the right side, so we used x, y, and r to show that cotan theta equals cos theta over sine theta. The next one, cos squared theta plus sine squared theta equals 1. Cos theta equals adjacent over hypotenuse. which from our circle equals x over r. If I solve for x in this case, we have cos theta equals x over r. I want to solve for x, I would multiply both sides by r. Then the r's divide out on this side, and I would get x equals r times cos theta. Do the same thing for sine. Sine theta equals opposite over hypotenuse. From the circle, that is y over the radius. If I isolate for r, I would have to multiply both sides by r, and then I would get the r's divide out on the right, and we get y equals r times sine theta. Then in Pythagorean theorem, for this triangle in this circle, we have the side x squared plus the side y squared would equal the radius squared. But we said right here that x is equal to r cos theta, so we put that in. R cos theta squared plus, and y is equal to r sine theta, so we sub that in for y. R sine theta squared equals r squared. Then we simplify, so the first bracket becomes r squared cos squared theta. Second bracket, so plus r squared sine squared theta equals r squared. And then we can factor out r squared from the left side. R squared times cos squared theta plus sine squared theta equals r squared. And then we can divide both sides by r squared, which divides the r squareds out here and divides the r squareds out here. So we get cos squared theta plus sine squared theta equals r squared divided by r squared is 1. So we used x, y, and r to show that cos squared theta plus sine squared theta equals 1. Use the fundamental identities to express each of the following as a single trigonometric ratio or as a single value. Tan x cotan x plus sine x cosecant x. Remember that tan x and cotan x are reciprocals, so tan x times cotan x can be written as tan x times 1 over tan x plus sine x times cosecant x. Remember that sine x and cosecant x are reciprocals, so we can write this as sine x times 1 over sine x. Then in the first term, tan x divides with tan x, and we're left with 1. And in the second term, sine x divides with sine x, so we have plus 1 again, so we get 2. Which means the expression tan x cotan x plus sine x cosecant x is equivalent to 2. Cos cubed theta plus sine squared theta cos theta. I should see right away that I have a common factor. In both of my terms, I can factor out a cos theta. Then I'm left with cos squared theta plus sine squared theta. But if I look back to my formula sheet, cos squared theta plus sine squared theta, that equals 1. So I can replace cos squared theta plus sine squared theta with 1. Then I get cos theta times 1, which just equals cos theta. sine x plus cos x all squared minus 2 sine x cos x. Let's multiply out the binomial. So we're doing sine x plus cos x times sine x plus cos x. And then we have minus 2 sine x cos x. Sine x times sine x is sine squared x. Sine x times cos x is plus sine x cos x. Cos x times sine x is plus cos x sine x, and then cos x times cos x is plus cos squared x, and then we have minus 2 sine x cos x. Then these two terms, sine x cos x and cos x sine x, they're the same because multiplication is commutative. So we have sine squared x plus 2 sine x cos x plus cos squared x minus 2 sine x cos x. And then we see that we have plus sine x cos x and minus sine x cos x, so those add to 0, and we are left with sine squared x plus cos squared x. But we just saw in the last question on our formula sheet, sine squared x plus cos squared x equals 1, so the whole expression simplifies down to 1. Tan x minus 1 over 1 minus cotan x. Remember that tan x and cotan x are reciprocal trig functions, so I can write tan x minus 1 over 1 minus 1 over tan x. Then I can simplify the bottom of the fraction, so tan x minus 1 over, I want to write 1 as a fraction with tan x on the bottom, so multiply top and bottom of 1 over 1 by tan x, I would get tan x over tan x minus 1 over tan x. The top is still tan x minus 1. Can combine the fractions on the bottom, we get tan x minus 1 over tan x. Then I'm dividing by a fraction, so I can multiply by the reciprocal of that fraction. Tan x minus 1, all of that, times the reciprocal of tan x minus 1 over tan x, which would be tan x over tan x minus 1. And then we have tan x minus 1 on top and tan x minus 1 on bottom. Those divide to 1. We are left with tan x. Verifying identities numerically and graphically. When verifying an identity, treat the left side and the right side separately and work until both sides represent the same value. Remember, this verification does not prove that an identity is true for all values of the variable, only for the given value. To prove that an identity is true, you must use algebraic operations to show that the left side is always equal to the right side. When proving an identity, be aware of the NPVs on the variables. The NPVs of an identity are determined by finding the restrictions throughout the entire proof. An identity can be verified graphically by sketching the functions that correspond to each side of the identity. The graphs coincide, so the identity is verified over the domain shown. Example, verify the equation 1 plus tan squared x equals secant squared x numerically for x equals 3 pi over 4. On the left side, we have 1 plus tan squared. The x value is 3 pi over 4. We need to determine the value of tan of 3 pi over 4. The fraction is 3 pi over 4. We can't simplify that, so we have a denominator of 4, which means our reference angle is pi over 4. And this terminal arm would be in quadrant 2, since the positive y-axis is pi over 2, which is equivalent to 2 pi over 4. And then the negative x-axis is pi, which is equivalent to 4 pi over 4. Then 3 pi over 4 is halfway between those, so right here. And the x and y values for reference angles of pi over 4 are root 2 over 2 for the x and the y. In quadrant 2, x is negative, so negative root 2 over 2, positive root 2 over 2. Then tan of 3 pi over 4, tan is opposite over adjacent, which is the y value, root 2 over 2, divided by negative root 2 over 2. Since we're dividing a number by its negative, we would get tan of 3 pi over 4 equals negative 1. So we can simplify the left side down to 1 plus negative 1 squared, because it was tan squared 3 pi over 4. Negative 1 squared is positive 1, so we get 1 plus 1, which equals 2. Then the right side is secant squared theta, so secant squared 3 pi over 4. Secant is the reciprocal of the cos function, so we can write this as 1 over cos squared of 3 pi over 4. Then we need to determine the value of cos of 3 pi over 4. Cos of 3 pi over 4. That equals the x value. Cos is the x value on the unit circle. And we saw that that was negative root 2 over 2. So then we get the right side equals 1 over negative root 2 over 2 squared, because it's cos squared of 3 pi over 4. We square this and we get 1 over 2 over 4, which equals 1 over 1/2. And then we are dividing by a fraction, so we can multiply by the reciprocal. We get 1 times 2 over 1, which equals 2. So then the left side equals the right side, which means we've verified the equation for the specific angle of 3 pi over 4. Verify that cos squared theta equals sine squared theta plus 2 cos squared theta minus 1 for theta equals 300 degrees. The left side, we have cos squared theta, which is 300 degrees. We need to determine cos of 300. Draw our unit circle. 300 degrees is 60 degrees less than a full rotation. So our reference angle is 60 degrees, and our angle theta is 300 degrees. Then at 60 degrees, I always remember it by which one is 1/2. Well, I can see from my reference angle, that my x value is going to be 1/2. My y value is much closer to the edge of my circle. So x is 1/2. And in quadrant 4, y is negative, so negative root 3/2. Cos is the x value, so cos of 300 degrees is 1/2. Then cos squared of 300 is 1/2 squared, which equals 1/4 or 1/4. And on the right side, we have sine squared theta, which is 300 degrees, plus 2 cos squared theta, which is 300 degrees, minus 1. Sine squared theta is the y value. Sine 300 degrees, in this case, that is negative root 3/2, so negative root 3/2 all squared, plus our cos was 1/2, so we have 2 times 1/2, and then that fraction is squared, and then we have minus 1. Square the first fraction, we get 3/4, plus 2, square the second fraction, we get 1/4 minus 1, which gives us 3/4 plus 2 times 1 is 2/4 minus 1. 3 plus 2 is 5/4 minus 1. We can write 1 as a fraction over 4 by writing 5/4 minus 4/4. 4 divided by 4 is equal to 1. 5 minus 4 is 1/4. So 1/4 equals 1/4. We verified the equation for the specific value theta equals 300. If an identity has a denominator at any point in the proof, you must state the restrictions. Restrictions should be stated as a general solution in terms of the variable. All tangent, cotangent, secant, and cosecant functions have NPVs. The tangent ratio, tan x equals sine x over cos x. Then our NPV would be that cos x cannot equal to 0. When does cos x equal to 0? That is when the x value equals 0 on the unit circle, which is at the positive y-axis, so 90 degrees, and the negative y-axis, so 270 degrees, and so on as we go around and around. So our general solution for when cos equals 0 would be 90 degrees plus 180 degrees, n, where n is an element of the integers. In radians, 90 degrees is pi over 2 plus pi n, where n is an element of the integers. Secant x is 1 over cos x, so again our NPVs would be that cos x cannot equal to 0, we can't divide by 0, so again it would be 90 degrees plus 180 degrees, n, where n is an element of the integers, or in radians, pi over 2 plus pi n, where n is an element of the integers. Cosecant x is the reciprocal of sine x, so 1 over sine x. Then sine x cannot equal to 0. When does sine x equal 0? Sine is the y value on the unit circle, so that is at the positive x-axis and the negative x-axis, which is 0 degrees and 180 degrees. So the general solution for when sine x equals 0 would be 0 degrees plus 180 degrees n, where n is an element of the integers, or just 180 degrees n, where n is an element of the integers. And in radians, we would have 0 radians plus pi n, where n is an element of the integers, or just pi n, where n is an element of the integers. And cotan x equals the reciprocal of tan x. Tan x is sine over cos, so cotan x is cos x over sine x, which means that sine x cannot equal 0. So again, our general solution for when sine x equals 0 would be, this time I'll just write it as 180 degrees n, where n is an element of the integers, and radians would be pi n, where n is an element of the integers. Consider the equation tan x sine x plus cos x equals secant x. Numerically verify that the equation is true when x equals pi over 4. The left side is tan x, x is pi over 4 in this case, so tan pi over 4 sine pi over 4 plus cos pi over 4. We need to know the values of sine, cos, and tan at pi over 4. We can draw our unit circle. Pi over 4 is one of our special angles here in quadrant 1, and the x and y values are the same for reference angle pi over 4, and in quadrant 1 they're the same sign as well, so root 2 over 2, root 2 over 2. Then cos is root 2 over 2, and sine is root 2 over 2, and then tan of pi over 4 would equal 1, because we're doing sine divided by cos, which is root 2 over 2 divided by itself, which gives us 1. So we get 1 times root 2 over 2 plus root 2 over 2, which gives us root 2 over 2 plus root 2 over 2, which gives us 2 root 2 over 2. Divide out the 2's, and we get root 2. On the right side, we just have secant x, and x is pi over 4 in this case. Secant is 1 over cos, so 1 over cos of pi over 4. Cos of pi over 4 is root 2 over 2, so 1 over root 2 over 2. We are dividing by a fraction, so we multiply by the reciprocal. 1 times 2 over root 2, which gives us 2 over root 2. Then we can rationalize the denominator by multiplying top and bottom by root 2, and we would get 2 root 2 over 2. And then we divide the 2's out to get root 2. So the left side equals the right side for this specific angle of pi over 4. B, how can you verify it graphically with your calculator? We want to verify that the left side of the equation is equal to the right side of the equation for the x value pi over 4. So in our calculators, we're going to graph y1 equals the left side and y2 equals the right side. And then we would check that the graphs intersect when x equals pi over 4. Up our graphing calculator. We need to make sure that we're in the right mode. So this question is in radian mode. Go to mode. I am in radians already, so that's fine. Hit exit. Then I want to go to y equals, and I want to graph the left side of the equation, which is tan x, move out of the brackets, times sine x, move out of the brackets, plus cos x. And then y2 is secant x. We don't have a secant button, but we can use the reciprocal 1 over cos x. Graph that. I'm going to change my window, zoom standard. And here's what I get. Right now I only see the red graph. If I go back to y equals, red graph is the right side. I'm going to turn that off just by hitting enter. Now it's turned off. And then I'm graphing just the blue graph, which is the left side. Graph that. Okay, now I see the blue graph. If I go back to y equals and I turn this one back on, now I should see both, graph it, and I only see the red one. So why would it be that when I graph both of them, I only see the red one, but if I just graph the blue one, then I see the blue one? Well, that would be because the two graphs are laying on top of each other, so they're identical and intersecting at all points. Therefore, they would have to intersect at pi over 4 as well. So we can say the graphs intersect at x equals pi over 4 since they intersect at all permissible values of x. So any point on the graph that is defined, the two graphs are intersecting. They're laying on top of each other. Another way that we can check this is to find the value of each of the graphs when x is pi over 4. So the easiest way to do this, I would say, would be to go back to y equals, turn off one of your graphs. So I'm going to turn off the red one. So I just have the left side, graph that, and then I want to find the value. So second trace, number 1 for TIs. For Casios, you do F5, and then I believe it's F6 for more options. And then it says xcalc and ycalc. We are calculating a y value, so you do ycalc. And then just like this, it'll ask you to enter an x value. So we're entering pi divide 4. And it's going to tell us the y value when x is pi over 4, which is 1.4142 ... So we can write, or find the y value for each graph when x equals pi over 4 and check that the values are equal. So for the left side, we have that x is pi over 4 and y is 1.4142 ... And then for the right side, x equals pi over 4. Go back to our y equals. Turn the blue graph off now and the red graph on. Graph it, then do the value again. So second trace number 1, or for Casios, F5, F6, and then ycalc, and then enter your x value of pi divide 4. and it tells us that y equals 1.4142 ... So the two y values are equal, which verifies graphically that the two sides of the equation are equal when x equals pi over 4. Algebraically prove that tan x sine x plus cos x equals secant x is an identity. State NPVs as a general solution. This is the same question as the last one, but in that one we were just verifying it for a specific value of x. When we graphed it though, we saw that the two graphs were exactly the same, which means the identity must be true. So now we're going to show algebraically that it's true for all values of x, and of course we need to state our NPVs when proving something that has any fractions in it. On the left side we have tan x sine x plus cos x, and on the right side we have secant x. I'm going to manipulate the left side until it equals secant x. So tan x is sine x over cos x times sine x plus cos x. That gives us sine squared x over cos x plus cos x. I can write this over 1 and then multiply top and bottom by cos x so that I get a common denominator. Then we get sine squared x over cos x plus cos squared x over cos x. Combine it in one fraction, we get sine squared x plus cos squared x over cos x. But on our formula sheet, we have that sine squared x plus cos squared x equals 1. Then we have 1 over cos x, and 1 over cos x is the reciprocal of cos x, and the reciprocal of cos x is also called secant x. So we get that the left side is equal to the right side. Now our NPVs. On the left side we had tan x, which is sine x over cos x. So cos x cannot equal to 0. And then we get down to secant x on the left side, which is also what we have on the right side. Secant x is 1 over cos x. So again, we get that cos x cannot equal to 0. When does cos x equal 0? Cos x is the x value on the unit circle. So when does that equal to 0? That would be at the y-axis, so at pi over 2, x equals 0, at 3 pi over 2, x equals 0. Therefore, x cannot equal pi over 2 plus pi n, where n is an element of the integers. Express cos squared theta plus sine squared theta equals 1 as the equivalent identity 1 plus tan squared theta equals secant squared theta. 1 plus tan squared theta equals secant squared theta. That's equivalent to 1 plus sine squared theta over cos squared theta equals 1 over cos squared theta. So let's start with cos squared theta plus sine squared theta equals 1 and see if we can get to this, which then gets us to this. So I see that I have a denominator of cos squared theta in 2 of the terms over here. So I'm going to multiply all of this expression by 1 over cos squared theta so that I can get that same denominator. One over cos squared theta times cos squared theta plus sine squared theta equals 1. The first term becomes cos squared theta over cos squared theta, plus the second term is sine squared theta over cos squared theta, and the third term is 1 over cos squared theta. The first term, cos squared, divides with cos squared, we get 1 plus sine squared theta over cos squared theta equals 1 over cos squared theta. And then we have the same thing here as we have here. Sine squared theta over cos squared theta is tan squared theta, so 1 plus tan squared theta, and 1 over cos squared theta is secant squared theta. So we get 1 plus tan squared theta equals secant squared theta. And we have to state our NPVs. The fractions that we had come from here, tan and secant. So we have denominators of cos. And over here, we only ever have denominators of cos. Then we would say cos theta cannot equal 0. So again, theta cannot equal pi over 2 plus pi n, where n is an element of the integers. That brings us to the end of Chapter 6, Lesson 1.